Welcome to part 3 of my coverage on naming organic compounds. And here, we go advanced, meaning we pay more attention to details rather than the fundamental rules. If you want to know more of the basic rules, go to parts 1 and 2. But here, we have a lot of special cases, a lot of considerations that we have to know in order to fully name some examples of organic structures. In this segment, because I will be dividing part 3 into many segments, we will try to discuss cases wherein the parent chain is not as obvious as it seems. And we will discuss those issues as we go through the different examples. So, let's get started right away with number 1. So, let me ask you to do this first. Determine the parent chain. If you are someone who has just watched part 1 and 2, you would say that the parent chain is benzene. And that's reasonable because all this time, all we know is that the parent chain is the longest one. But now I would like to introduce you to the set of considerations here that show us that length is not the only consideration in determining the parent chain. In fact, rule number 1, which is the most powerful rule of all, states that among all other rules, the parent chain is one which contains the principal group. Going back to number 1, the principal group is OH. And since OH is attached to this ethyl part, or this 2-carbon chain, apparently this is our parent chain. We write that as ethanol, because that's 2-carbon single bonds OH, right? And if you know your locants, this is number 1, this is number 2, meaning that benzene is not actually a parent chain, but it's just a substituent located at number 2. And we write that as 2-phenyl. I'm just saying that longest does not automatically mean parent. For 2, we have another dilemma because not only do we have 2 compounds that have no principal group, so meaning you cannot anymore use rule number 1, they are also of the same length. Look at the cyclic part. How many carbons do we have? 1, 2, 3, 4, 5. Look at the linear part. How many do we have? 1, 2, 3, 4, 5 as well. So meaning, you really have a problem here, like you're going to ask yourself, I always knew that the longest is going to be the parent, but here, what if I have equally long parts? This is going to answer the question. If there are 2 candidates, one is cyclic and one is not, the cyclic part would be the parent. So this would be our parent. We write that as cyclopentane. And of course, the pentane part will be written off as just a prefix or a substituent. We don't go the other way around. In number 3, this is even more confusing than 1 and 2 because my 2 candidates for parent, look at this. This is ethane, and then this is, well, also ethane. So this is confusing because you have 2 candidates that are exactly the same. And therefore, since they are the same, you cannot anymore choose the longest because they are equally long. None is cyclic. Of course, therefore, there is no homo or heterocyclic part in number 3, and there's also no principal group. And now you turn to consideration number 5, saying that whichever here has more substituents of low priority like alkane or alkoxy or halo groups would be the parent. So let's just call this left ethane and this as right ethane. If left ethane is the parent, its substituent would be everything at the right, only 1. If right ethane is the parent, it would have 2 substituents, this chlorine at its right and this alkoxy group at its left. So 1 versus 2 substituents, we choose right ethane as our parent. And what are its substituents? Chloro at this carbon, and if you know your naming, this is ethoxy at this carbon. Of course, we know that alphabetization is going to be the consideration for locant assignment here, 1 for C and 2 for E. So we write that as 1 chloro, 2 ethoxy, ethane. For number 4, as well as number 5, notice that we already have here heterocycles. And since I haven't discussed heterocycles in detail yet, I already wrote their names as well as their locants so that we will not concentrate on them. I want to concentrate on the parent assignment, okay? So for example, in number 4, Our rule number 1 is always to find the chain with the principal group. Well, this benzene and this pyridine group, they both don't have any functional group that is principal. So we go to rule number 2, saying that a hetero ring will be preferred as the parent over a homo ring. Pyridine is heterocyclic, benzene is homocyclic, meaning that this is our parent. And therefore, benzene is once again a substituent located at number 2 of pyridine. So we write that as phenylpyridine, specifically 2-phenylpyridine. How about in number 5? Do you follow the same principle? Like, oh, furan is heterocyclic, so this must be my parent. No. Look at my approach. I always go to number 1 first. Is there a principal group in furan? No. Is there a principal group in this cyclohexane? Yes, right? This is a carbonyl group. In fact, the functional group here really, or the pattern here is RCOR, ketone. So here, even though this is homocyclic, who cares? It contains a principal group. So this must be our parent. So I hope you are already getting used to or observing how to use this set of rules. So this is our parent, cyclohexane, right? And then the suffix for ketone is ONA. And if this is carbon number 1, this is carbon number 2. Therefore, furan is just a substituent at number 2. So that's 2-furan 3-il. Don't worry about the 3-il, like, what's 3-il? I'll discuss what this once again in another video for heterocycles, okay? But the point is the parent is this one, because principal group. Finally, number 6, I made this as the last example because we will be able to exhaust all possible considerations. Here, the candidates for the parent are both benzene. And that's a big problem. Why? Because both are homocyclic, cannot use 2. Both are equally long, cannot use consideration 3. Both are cyclic, cannot use consideration 4. And both don't contain any principal group. Okay? And then, if you look at number 5, which has more low priority substituents, if I think of this as my parent, I will have only one substituent. If I think of this as my parent, guess what? I will also have only one. So like, you can't even use number 5. And your last resort, in real life, we rarely ever get to this point, but our last resort is alphabetize them. Like, name them completely and then choose the one which wins by alphabetization. How do I do that? Let's try doing this as the parent. And then let's name the substituent. Remember that when you name a substituent that's composed of many substituents, you name from the part farthest from the parent going to the parent. So if I do that, we will name this like phenyl methyl oxy, or I can write that as phenyl methoxy. And if I go the other way around, let's say this is my parent, benzene. If I go from left to right, it will be phenyl oxy methyl. And if I shorten that, that's phenoxy methyl, right? And in fact, these two are still strikingly similar, but there is a difference still, right? So you try to cancel all the similar letters at the left, and then try to find the first point of difference. So as you can see, this is our difference, Y versus O. So since O comes first in the alphabet, then this must be our preferred choice, the violet one. Once again, we rarely ever get to this point, but I'm just demonstrating just to show you that it can happen. So these are the many considerations for choosing the parent, and I hope that you realize as I end this recording that length is not always the primary consideration.